session on agent-based modeling and social network analysis. This is already the third time. So we started on Tuesday, and we also had a session yesterday. This is a session organized together with Federico Bianchi, University of Milan, Filip Agneessens from the University of Trento, and Andreas Flache from the University of Groningen. So welcome everyone. And we also, just like and the other days, we have one invited speaker and the regular speakers afterwards. And the invited speaker is my pleasure to introduce you, Per Block from University of Oxford. And the floor is yours.
Okay, thank you very much. Let me do this and okay, can you see my screen? Perfect. Yes. Okay, well, thank you very much for the invitation. As I said, I'm Per. I'm in Oxford at the Department of Sociology, which also hosts the newly founded Leverhulme Center for Demographic Science, which is my main affiliation. So I'm not a native agent-based modeler, but most of my time I spent doing empirical network analysis. And that means when I was invited to give a talk, I don't feel like I'm in the position to give you high-level philosophical ideas of how we should do ABMs and networks, but rather I'll present an actual study that I think fits very well with the theme about incorporating network logics or incorporating network ideas into agent-based models, or the other way around, incorporating agent-based models into network analysis concepts. So this study actually came out of this brief period early this year when everybody applied their subject knowledge to COVID. So, and this is also what we did with my colleagues when this started to dominate our lives. We sat together and thought about whether there's anything meaningful we can contribute rather than just some data wrangling that seemed to be the standard, but whether we can really use and contribute our network knowledge. And since I did some disease modeling with networks in the past and have some brilliant co-authors, we came up with a study that I'll present now in the next couple of minutes. Now, one thing about the presentation is I'm going to present a published paper, which has advantages and disadvantages. On the plus side, if something's unclear, you can read up on it. It's quite polished, and you can just sit back and relax and enjoy. The disadvantage is that some of you might have read it, though I guess that's not going to be many people. And even for them, I hope there's some interesting details, because in the paper we can't go into the things that actually find most interesting. And the other disadvantage, I won't be able to deal with any constructive feedback, or also not constructive feedback, but I guess I wouldn't have dealt with it anyway. So this basically is the paper. And I'm mainly showing you, so I just heard that we don't have really the, give me a second, I want to do this. So up here is the DOI, if you want to see it and look back at the video, but I also want to show you just once the name of my co-authors who really did an awesome job, especially Marion Hoffman, who did a lot of the implementations of the models and the simulations with me, but also all the rest really did brilliant work. So before I actually go into the presentation, I want to give you a brief, like an abstract of the paper, the basic message, what we do. And we started out with the idea that basically this whole lockdown thing is not a lot of fun. We're not really happy to sit at home and do nothing, all of us. But for some, it's even more critical. We have like psychological problems arise with sitting at home. We can have economic damage. Many people, or some people, have unsafe living conditions or living situations, which makes a lockdown really unhealthy. So our basic idea behind this was, how can we keep up a semi-normal life, or how can we keep up some sort of social contact to overcome these problems during such a pandemic when there's a virus outside that tries to kill all of us. Now, the basic idea we have is we understand how diseases spread through networks. We can try to restructure our social networks in a way that the spread is significantly slowed or completely curbed. And we can do this in such a way that we give people, we only rely on local knowledge. So we don't need to have a bird's eye view of overall network structure to do this, but we can tell people, just looking at their surroundings, what they can do to really make network structure much more, to change in a way that is much easier for us. And in particular, we can look at how it works if we recommend people to stay close to themselves, or to stick with people that are similar in some way, if we limit our context to few others, and specifically if we avoid meeting people with non-embedded ties. And all of this we can do based on simulations. So, having said this, let's go actually into the presentation itself and start from the beginning. So we know that this is a disease, or that many of these diseases are passed on through interpersonal contact, right? We need to be close to each other. None of you will get infected if I'm infected at the moment, so we need to have the physical proximity. And so, of course, this means the more people we meet, the more people you can infect. And the idea of social distancing that is broadly, I think, still applies in most places of the world, is the fewer others we meet, the fewer we infect, right? And this basically means I think it's called flattening the curve, or basically we spread out the incidence of cases over longer times and try to have fewer people infected overall. Now, something that has a particular, now I can see it. Something that has the particular network logic to it is that not only the amount of contact or the extent of how many people we meet, but also the structure of who is in contact with whom determines this type of infection curve. And this is something that I want to, something that I want to illustrate now with a live ABM. So we'll do some live agent-based modeling now. So basically imagine this is a contact network. So all these lines are people being in contact with others. The color of these lines basically is only to highlight the community structure. They have nothing different. And let's think of a very simple model where we start. This is our nice community, and one person is a seed node of being infected. Let's say this is the person who just came home from the party weekend in Ibiza. And now we look at basically a round-based simulation, how this disease will spread through a network if everybody infects everybody they're in contact with in every round, right? So we have the first round, and then our seed node infects everybody he or she is in contact with, right? And this is these 4 people. Then in the next round, the second round, we see all of the contacts of our newly infected ones now become infected. So at round 2, this person, this person, this person, this person, this person, this person, and this person become infected. Then we go on with our simulation. In round 3, we have the person here, this person, all contacts of that person are these, all contacts of this person are these, and then here we have basically this whole cluster. This is after 3 rounds, and after 4 rounds, to make it very quick, here, all of these are infected, and this person, this, and this, and this. So basically after 4 rounds, of this simulation, well, it's called an agent-based simulation, basically the entire network, or almost the entire network, is infected with a disease. Now, if we take the same people and restructure or reshuffle the structure with which they are connected, we can come up with something which basically is just a normal grid. Right? Here we have the same amount of people, and we have the same number of average contacts, right? So the prevalence of contact is the same. And if we start again with somebody here being a seed node, and we run the same simulation, we see after the first round, these people are infected. After the second round, it's these people. After the third round here. And after the 4th round, these people here are infected, right? So after the 4 rounds, we can say that this half of the network is infected and this half is not. So we see that despite having the same prevalence of contact, the level of disease spread is quite different, and we can go even further and look at this network. And this network also has the same number of nodes and the same number of ties. But if we infect anybody here, and the nice thing here, it's completely symmetric, it doesn't matter where we start. We see in the first round, these are infected. These people would be infected in the second round. This is the third round. And this is the 4th round. So basically after 4 rounds, now we are in a situation where quite a bit, well, no, it's not so easy to draw with a mouse. We see that in this, quite a bit fewer than half of the population will be infected in this scenario. And this is just a very intuitive way of telling you, and I guess most of you know this, that it's not only the amount of contact, but we can change the structure in such a way that we have very different outcomes in terms of disease spread. And now here I have basically the same thing, but with a nicer video where you don't see me drawing something with a mouse straight away. But we see two different types of networks, again, the same number of nodes and same number of ties. And we have here, now it starts, we have in the middle this seed node, and then the infection spreads through the network. So we have here these orange ones are the ones that were infected, the red ones are the ones infected. The next step, and let me show you this again. So basically now you can see the red disease spreads throughout the network. And now what we did is, once the simulation is done, is we color the nodes by the amount of time, how long it takes until they were infected. So this dark blue color, these nodes here, they were infected after 10 steps. And we can see this curve here is much flatter and is much more drawn out, and this is much steeper. And something quite crucial here is we could also rename this diagram, not saying the number of newly infected individuals, but we can also say this is a histogram of network distance from our source node. So we have 3 people here who are at network distance 10 from our source node. So we can see that the further you are away, the longer it takes, and the longer the average paths are in our networks, the flatter this infection curve is. So this is basically one of the basic ideas or the basic intuitions that we use in our modeling or in this paper, on this study, that networks where paths are long are those in which a disease spread is slow. And yeah, I'm basically just repeating this again. The general of the idea is we want to form or reform networks in the real world so that contact patterns look more like this lower network where it's long drawn out than this upper network. So we basically try to manipulate our network structure. And I think I already said this too. Path length in the network directly maps onto the extent or the speed of disease spread, so this infection curve. And although this is something where you'd say, of course, this is obvious, we know this, I surprisingly found no discussion of this in the literature so far. And the next idea or the main point of this study is that people can choose among their contacts who they want to cut out of their actual meetings, or who they want to stop meeting, so that we can create these networks with long paths. And it's about these different types of strategies that people can vary that I'll talk about. So, yeah, okay. And the fact that we can give people these sort of strategic recommendations basically gives us an opportunity for intervention, which can be better than this complete lockdown because we just reduce ties rather than telling everybody to not do anything at all. And to give you another illustration here, we have here or an illustration of these strategies. Here we have basically a small world network, or this kind of connected caveman structure that I think was first suggested or presented. I know it from a paper by Watts about 20 years ago on small world networks in the AJS. So basically you have these small communities. Within these communities, people are very similar, indicated by the same color. So basically here's a reddish, orange, yellow, greenish, green, bluish, and so on. So you have a lot of connections within these clusters and few between them. And we can also think that the location of the nodes in the graph relates to, say, a geographic position with it. And now what can we do to make networks paths longer here from the perspective of the actor? Down here, where the circle is now, we have basically a bar chart of distance from these infection seeds nodes, which is this one and that one, right? So a few are directly neighbors, but most of them are distance 2 or 3, and very few are distance 4+. So the first very easy thing to do to make networks paths long is decrease long-range ties. So long-range ties are those that live very far away, ties that actually are long in the graphic, that are live very far away, but we can also see these are ties between actors that have a very different color, which can indicate, or which is indicating that they are very different on some core attributes. So we can see that this already decreases network path lengths quite a bit. So this already drags out this infection curve. What we can do, apart from recommending to limit ties to those who are more similar or who are geographically closer, is we want to discourage ties that are bridging ties, right? Because we know that bridging ties, those between clusters, are the ones that really reduce path length. So this is the basic idea behind the small world phenomenon, that very few of them really make the network paths very short. And basically we can see here that if people drop the ties that are not embedded within cycles, within 3 or 4 cycles, which is a local configuration we generally think that people know if their friends are also friends with each other, then we can again increase the path length and therefore curb infection spread. And finally, if we go, if we make the last step and say, okay, we now agree that we basically form small groups of repeated interaction within these groups, we can do this even more. So we basically have 3 ideas. We want to think about similarity between actors or geographic closeness. We want to think about the embeddedness of ties, and we want to think about repeating contact with others to make network paths long. So basically now you have the theoretical or the intuitive part of this model, and now we apply this or move this model to an ABM. So this agent-based model has a few parts. First of all, we know that individuals are linked through some sort of network of potential contacts. And these are the types of networks that we usually measure. It's anything from friendship to acquaintanceship or so. This is basically the group of people that I could potentially meet, right? It can be my friends, my family, my coworkers, all of these. But it's clear that I don't run around the city here and knock on strangers' doors and try to meet them, but I meet up actually just with a relatively small number of people over it, right? So basically we need this type of underlying network, and then we make strategic choices of who people want to interact with. And here we call it a unilateral choice with whom to interact based on some of these strategies. And this is where we can implement our variations to see what happens if people choose the interaction partners on different bases. And then third, what we do is in these meetings that are based on choices, infections occur in an SEIR model fashion. So it's also kind of a model. Now, what is the SEIR model? It's a compartment, it's a standard model in disease spread, and SEIR stands for susceptible. So basically it's all the people that have never had the disease so far. Then we have people that are exposed, and these are the people that are already caught the disease but are not yet infectious. So it's the time before you develop symptoms. Then it's the infectious people. Those are go around and give it to other people. And after some time, you're not infectious anymore, but you are removed. And removed means can be recovered, can be dead. Usually people tend to call it recovered because that sounds nicer. Now, starting with the first part of our the first simulation, we need to generate these stylized network models because we don't know contact patterns within a larger population. We have some ideas and we have good indications or intuitions about how these networks look like, but we don't know this fully. So we need to simulate basically large-scale networks of many people. And we do this with different sub-processes that then give us our overall network organization. And what this does is, first of all, we assign people to in a 2D grid to some geographical locations and give them ties that are close to themselves. So people are mostly related to others or have contact with others that are close to them. Then we put people in some sort of organizations, which can be schools, companies, families, and so on, and then people form ties. Within these organizations, we assign people attributes, and people form ties to others who are similar to themselves on these attributes. And we add a certain number of random ties between people, and this overall gives us a network that gives us a network with the right parameterization that is quite realistic in terms of clustering coefficients, degrees, and so on, what we know from networks. And we, of course, have the ability to vary lots of parameters to make this network have some different characteristics to see how robust it is to our assumptions. Okay, now that we have this network, this gives us the opportunities for contact. And based on these opportunities, people now make choices with whom they want to be in touch. And this second model, or this simulation model of these choices, works like this. So basically, this is only the outline. We have everybody is in a susceptible state, and then somebody is a seed node, and we are at the beginning of the simulation, right? So this is the outline. What happens? Time moves on, and we pick some individual, I, randomly from the population. And this individual then decides to contact a neighbor or not. And here we add this step that an individual can contact the neighbor or not. So we can look in the model, what does just general contact reduction, how does that lead to different outcomes? Now, if this individual decides to contact somebody, the question is, whom do they contact? And here we have a neighbor J is chosen with a certain probability, and this is where we can implement these interaction strategies. And then after a J is chosen, we can say if either I is infectious and J is susceptible, or the other way around, then infection occurs. The one that's infected infects the others who is healthy. And then afterwards, we move on to letting time pass. So people that have been exposed become infectious. People can recover over time. So we just look on and then see if there's anybody left who is still in a susceptible state. And if nobody's left, then we end the simulation. And otherwise, we keep going and we keep choosing a person that interacts, that infects, and that basically is our disease dynamic. Now, an important part is this here. How is a neighbor chosen? Here we have the probability of choosing J, and basically it's a chosen according to this formula. And those of you who know about stochastic actor-oriented models will have seen this formula to you will be immediately obvious, because it's basically the same idea. We have a multinomial choice model where the probability of I choosing at J is a function of a statistic, and this formalizes some sort of relation, and a statistical parameter, which says I'm more or less likely to contact this person. And it's the same that we normalize over all people. And I think one thing that we note here is we have normalized over all people that are in the neighborhood. So it's who do I choose of those in the underlying contact network. And this is where we can implement these strategies in our agent-based model. And we have here three that I mentioned earlier. Is we have a similarity statistic, and here we have this A being some sort of individual characteristic. We just say, is J more or less similar to myself? And down here we just normalize by the range of the variable. We can also have a statistic that looks at whether I and J have a lot of shared contacts. So this SISJ basically looks at shared contacts, and we have a statistic that looks at the repetition. So we basically can specify a model, and this parameter alpha here gives us the freedom to say I is rather going to choose some J who is more similar like them, has more similar contacts or more previous terminations. I think the interpretation of these parameters is not really relevant, so I'm going to skip this for now, but I go again to this flowchart. So here, this is the part where we model how do people choose their interaction partners, and this is where we can put variation in the strategies that people choose. And what we then do is we look at the outcome in the end. How do these different strategies of interactions lead to different infectious outcome? How many were infected, and how did these infection curves look like? What we do, and this is a brief side note, but I think it's very important. What we do is we normalize, because these parameters alpha for the different strategies are not comparable, we calibrate them so that the certainty with which they predict who somebody will choose is identical. So we say the strength of the parameter is the same, and we need to use some sort of entropy-based measure, and this is found hidden somewhere in an old paper on network evolution from about 20 years ago, that this is a way how we can look at the strength of the prediction of them. Okay, so basically now that we have this, we can compare if people just within the same network, if people interact normally, how would infection curves look if people reduce contacts, or if we use these different types of interaction strategies, how would our infection curves look? And this basically is averaged over a couple of thousand runs. We call this a baseline model because it has all the parameters we vary. This is kind of in the middle. And we have this blue line here is a model we call full contact model. Basically, this means if people just live a normal life in our model, how would these infections develop over time? And here basically within 15, 12 steps, we have most people being infected over time. And this black line here is our actual comparison scenario, which is more interesting. What happens if people just reduce the amount of contact they have, but do so in a random fashion? They just say, okay, every other time that I want to go out, I'll stay at home. And these are then basically ideas. What happens if people reduce their contacts, or if people make more strategic choices whom they want to interact with? And the pattern we see here is that usually this reduces the peak of the infection curve by about 50%, and a bit more, usually a bit more than 50%, reduces the number of total infected over time. And I am not confident enough to say that there's really a difference between these three lines. And I'll show you some variations here, but we generally see always a similar pattern, that they really reduce compared to this random part, the amount of infected a lot. So we vary lots of parameters to see how robust we are to variations. We vary the network structure, so we look at just how small world networks, how it would look on a grid, how it would look in random networks, and so on and so on. We change the network size, we change how likely it is to catch an infection interaction. We vary exposure times compared to times of infectiousness. We vary different ways how people can implement these strategies. We vary whether a joint implementation of multiple of these changes everything. And basically, our outcome is always kind of the same in all of these scenarios. We then have lots of these curves, and they all kind of look the same. They look the same, that we have this big blue, then the medium-sized black curve, and then this red, green, and yellow. These are the three colors: red, green, and yellow curves, having quite some, leading to quite a significant reduction in the amount of people that are infected. Now, of course, this is there are a lot of caveats to this model as a simulation model. I think this is not surprising. First, this works best if people does it. We model it as everybody follows the same guidelines, and I guess at the moment it seems that it's more likely in some countries than in others that some proper public policy that people stick to could be implemented. Of course, we have a toy model of interaction here, where we are very simple to look at how some sort of behavioral rules or strategies lead to different outcomes. And because we have this more toy model, what we do is we make a qualitative judgment. So we say relative to one another, which is better, doing this or doing that, being just meeting less people, or trying to look at who we meet. And here I think we can be fairly convinced by all the robustness checks we did that this does reduce the speed of which it spreads through a population, but it doesn't mean that we can make absolute judgments of saying, if you do this, then everybody's safe, or if you do that, then everything will be fine. So as the takeaways from here, we know that, and we explored more how contact networks and alterations of these networks can really contribute or be important in looking at disease spreads. We can alter networks, and I think this is for me one of the more interesting parts. We can alter macro level network features by giving people by changing networks only from the micro level point of view. So we don't need the bird's eye view on networks to change the factors that are most important for us. And I think in terms of in the context of this conference, a great thing is that it's all based on simulation. So we have basically we have all this insight just based on these different types of simulations that we implement. So thanks a lot for listening. I thank you for Marion for producing this this beautiful graphic. And as you can see, I placed myself as far away as possible from the dangerous virus here in the middle. So thank you.
Thank you very much, Per. Federico will help us to handle the Q&A.
So thank you, Per, very much. That was a very interesting presentation. We have 10 to 15 minutes, I would say, for Q&A. So we have a good room for discussion about this. There's people who have been writing down their questions in the chat while Per was talking. The first one, I guess, was Christopher Watts. Since I see, so why don't Christopher, if you want just to unmute and ask Per your question directly.
Yes, thank you. Okay, so you're showing us some very attractive toy networks there. I was wondering, how would you go about trying to translate this into the kind of question a policymaker is faced with at the moment, such as, do we close the schools or not? Or do we let the students go back to university? So I can't help feeling that a class of school children is rather a special kind of network, rather different from the kind of toy networks you've been studying there.
In a sense, yeah, yes, of course, it is. But so the little drawings and the pictures I showed you, they are for the intuition, right? So for the actual simulations we use a couple of thousand of nodes, and we manipulate these networks in a way that we find most sensible for our networks. So we could, of course, include in these simulations high-level school closures, so basically forbidding certain types of network ties to do this. This was not our primary motivation, though. Our primary motivation was more to look at more small-scale contexts. What's the kind of things what's the kind of small-scale interactions that we can allow people with keeping risks minimal. So sure, we can make recommendations, we can make secondary recommendations, and I'll keep this very short, secondary recommendations of saying within schools, you can say, keep classrooms separate from each other, reorganize school structures so that children in the same neighborhood are in the same class, stagger breaks, and all these things, you can transform them on the school level, but our direct simulation is not about this.
Okay.
Okay, then we have a question by More Atlas.
Hi, yeah, I was just wondering, how do you address the super spreaders or the opinion leaders if we're looking at diffusion models? So,
I mean, we don't need opinions. Because
so in the super spreaders, people who have many contacts.
So I mean, working with empirical networks for a long time, there's in normal face-to-face interactions, high-degree nodes were relatively irrelevant, right? And if you look at friendship networks, all these kind of things where people meet close face-to-face, you don't have massively large. You don't have these kind of people that have face-to-face contact with thousands of others. What happens is in large gatherings of, say, I don't know, concerts, football matches, things where a lot of people come together. And I guess that's beyond the scope of the model here to say, yeah, I think it's beyond of it. We can just say, well, this is something that you shouldn't do anyway. And we look at more the detailed, what's a reasonable way of structuring interpersonal contact rather than these massive gatherings.
Okay, so next question appears to be by Roger Cremades.
Thanks for the nice talk, Per. I could hear the word prediction when you were discussing the formula about the entropy. And after having a look at the paper, I would like to ask you what you meant by prediction here, and exactly in the paper you talk about the degree of certainty, and that what do you mean by the degree of certainty and by prediction in this case? It's a complicated question in the context of this conference, I know, but I think it's very, very, very nice to ask it. Thank you.
Yeah, no, thank you. I think I try to make this, it's a bit complicated. So I was imprecise, prediction was the wrong word here. Or maybe, so if you think I have the choice of choosing between 10 people I want to interact with, and if everybody has the same probability of receiving my interaction, then we have very little certainty, or basically no certainty in this probability model who I'll contact next, because everybody has the same the same relative probability. If though my probability says all probability mass is on one person and 0 on all others, then I have very high certainty what's going to happen next. Okay. Right? So if we just move between this case of very high certainty, we then code as a 1, we have no entropy in the system, or very low certainty where we have a very flat distribution, and then we have basically, and this is what I mean by prediction, if we run the model, how certain are the outcomes? And this is
very clear answer. Thanks a lot. It's a complicated subject. Thank you very much. I enjoyed hearing this.
Okay, now next one would be a question by Alejandro Espinosa Rada. But before, just let me remind everybody that you can, in the meanwhile, write down your questions in the chat, or maybe also use the related hand raising option in Zoom, or just using your actual hands. We should be able to spot everybody. So Alejandro, please.
Hi, I think you already answered one of the 2 questions, but have you thought about how to calibrate this model with empirical data? I think that would be my question.
Yes. I think that the biggest part of calibration would be actually getting underlying network data, because I think this is the point where we really need to calibrate it empirically, and then we can look at what behavioral changes do, because we can make these behavioral changes then based on assumptions. I think the underlying network would be tricky. And we thought about going down some different avenues. One would be with extrapolating from ego network data, from contact tracing data. You might be able to, if you start with a person that's infected and then names who they were in contact with, and then somebody else is infected and tells who they were in contact with, you get these small ego networks, and then you can extrapolate to larger level network structures with ego ergons, and that would allow you to do this. However, we didn't get any data of this sort so far, so we haven't got data yet to calibrate these models or to model it on actual realistic networks.
Okay, we've got a question by Srebrenka Letina. Srebrenka. Would you like to ask your question?
Yeah.
Great.
Yeah, thank you, Federico. So, I mean, it's not a question, it's just a suggestion. So we have been doing some research here on compliance behaviors, and it seems that there are 2 dimensions that are quite distinct. So one is social distancing, and the other is hygiene related with hand and so on. So I'm just suggesting that maybe for the future models, it would be nice to add this dimension and to see how this affects the spread of infection and changes the transmission probabilities of links and the whole outcome distribution. So just suggesting that maybe, in addition to social distancing, this other dimension, and that's hygiene related, should be modeled together and separately. That's all.
Thank you. I think the nice thing, I don't know if anybody wants to download the code that we have. It's somewhere up there. It's a bit, it's hopefully not too messy, but the way the model actually is implemented, and I rushed through it a bit, is that you have these different points that you can tweak, where you can change the probability of infection during a meeting. And this is, of course, if you make this heterogeneous to actors, you can, in principle, include these other types of behavioral changes like washing hands, wearing a mask. And if you include them, basically, the outcome would be a decreased probability of transmission within meetings. So it is possible to include this if you want to make the model more complicated, but we have not done this to well, focus very much on one specific aspect. But thank you for the comment.
Thank you for your answer.
We now have a question by Andreas Flache. Andreas?
Hi, yeah, thanks. Yeah, so I was wondering to what extent, let's say, the results you have about the different strategies depend on the assumption that people more or less accurately know the network they have, and especially the network of their network contacts. We know from empirical research that people are pretty bad in having accurate ideas about networks.
That is true, but we only need, so for some parts, I need to know your things about your attributes. And I guess some of these attributes are really quite easily visible. If I know where you live, if I know your some other attributes. So we need people to know something about the people they meet. This is one of the three. The second is, well, I hope I know the last 3 people I met. So this kind of repetition needs quite little. The only thing that needs some sort of network knowledge is networks of distance 2. And this basically doesn't mean distance 2, but it means that I need to know whether my contact partners are in touch with each other. So basically I need to know whether my parents know my work colleagues, or whether my friends from school know the people that I'm in a football club or whatever. Mm-hmm. So basically we need to only know who these close triangles are. And I think for many of these things, we have some relatively accurate knowledge, knowing which of these triangles where we are part of are close and which ones are.
Though, if I may follow up, this may be one of these cases where a small violation of that assumption could have big effects, couldn't it?
Yes, yeah. And it could, because these would be the bridging ties now. Of course, because we are in a modeling world, whatever we implement, also there's a lot of nuances to this. What we did in the actual agent-based modeling is the proportion to contact somebody was proportional to the amount of triangles that was embedded. So basically, I'm most likely to know the ones where it's a small group and everybody's in contact with everybody. So say my family. I know my parents, know my siblings, and so on. Right? So the model says I'm most likely to engage with those where there's a lot of these kind of triangles. And small violations would also mean relatively small differences in probabilities. Mm-hmm. This is for the statistical model or for the simulation model we do, which I guess is less prone to this. How this relates to the real world, where you need to make more concrete recommendations, where you can't really ask people to calculate the number of triangles and then make probabilities based on this. For the everyday interactions, it's possible that that violations here, erring on the side of assuming that there's contact when there's none, could be bad.
Okay. Thank you.
I guess we have just time for one very last question. I will read it out because otherwise we run out of time. Please, try to be as quick as possible. We have Rajesh Kumar Pandey asking you whether the Barabasi-Albert network model could be considered as a good model for contact networks.
No, very quick answer.
You
work
really
with empirical network data. There's absolutely no reason to assume any sort of power laws in normal human contact networks. This is not realistic.
Okay, so thanks for a very clear answer, and also for all the contributors with the questions, and especially for the very interesting presentation and lecture. So we have to move on as time is up. So our next presenter is Luca, for the same topic, basically related topic, COVID-19 related topic by Luca from Sorbonne and Trento. So the floor is yours.
Okay, can you hear me now?
Yes, no, it's okay.
All right. Well, thank you for inviting me, and thank you for listening to me. This is a joint work with Marco Albertini and Stefanie Scherer from the University of Trento, who's also my PhD supervisor. So the question we are asking, the title of the presentation is, do inter-age contacts explain cross-country differences in the diffusion of the COVID-19? And so, okay. Yes, so very from the outbreak of the disease, demographers made the point that no, okay, well. Yes, demographers made demonstrated that the population age structure of a country explains part of the cross-country differences in the case fatality rates. And so basically the idea is very easy to understand, is that countries with with an older population are more at risk than others. But then we rapidly noticed that this could not explain all cross-country differences, and started emerging the idea in the literature that intergenerational relations could play a role. And I think that the fact that Italy was the first European countries it was helped this idea to emerge. So the idea was like, not only do Italians have an older population, but also the elderly in Italy are more easily in contact, more often in contact with the grandparents are more in contact with their grandson or with their son, their children. And this could additionally, side by the age structure, generate more cases in the elderly in Italy. Okay, the problem is that this idea was there. Many papers mentioned it somehow, but it's really hard to empirically test it. There are many reasons why. I just would like to highlight a few. We would need a clear measure of the number of cases, something that wasn't possible at the beginning. Also a comparable measure between to allow for comparison between countries. And so you know that at first there were a lot of measurement issues, cross-country differences in the number and capacity to make tests. Then came into play the lockdowns, different lockdown strategies between countries. So it's really hard to see it empirically, to test this idea empirically. And then my co-authors had the idea that actually it might not just be the inter-age mix, the inter-age contact mix that matters, but also simply how many contacts do people have. Maybe it's just that the grandparents in Italy, they simply go to the bar to have a coffee, they meet among each other, they simply have more contacts. So we have these two ideas, these two hypotheses, like what could play differences, what could explain differences between countries would be the inter-age mix, or it could be the sociability of individuals. And this is what we are going to try to disentangle, and first try to see if networks, these two aspects combined, they have they could generate cross-country large differences. Do networks matter, basically? Okay, so we are going to use, we use a data source that is very, has been widely used for many models of infectious disease. It has the advantage of being comparative. There are several countries. And so we took Italy because of all the reasons that I mentioned, and Germany and Great Britain. You will see a bit why in a little bit. And so this kind of data, we have the information about participants who declare their age, the number of daily face-to-face contacts that they have, and the ages of these contacts. And this is what we are going to use to rebuild a sort of empirical network. Just before going into the ABM part, because that's how we are going to address this question, a few empirical, very basic things. So we just counted the number of, in the data, in the empirical data, we counted the number of ties between generations. And we see that indeed there are differences. Italy has more intergenerational ties compared to other countries in numbers, in the number of ties. But this is mainly due to the fact that Italians have much more ties, much more contacts than the two other countries, as we will see in a minute. So if you look in the proportion of how much these intergenerational ties represent in the proportion of total ties, it's actually quite comparable between countries. And so the second hypothesis was like the sociability, how much contacts do people have. And here, if we look at the empirical data, there is a lot of support for this hypothesis. It's very clear here. So on average, the Germans, they have 8 contacts, while in Italy, they have almost 20 contacts. And one could ask, is it compensated by the fact that the Germans have longer contacts, so higher probability of transmission for each of their contacts? And the answer is partly, but a little bit. So the average duration of contacts is a bit higher in Germany, but not so much. But we will take this into account still because it is important. So do we find empirical support for both hypotheses? Yes and no. A little bit for the interage mixing hypothesis, and a lot for the number of contacts, the sociability hypothesis. But the question now is, do these differences, do they lead to higher differences in the in the propagation of the virus? So for this, we are going to use our data to recreate a realistic network. I'm going to enter a little bit into the details of how we do this because I think it is important. So the first thing we do is like creating a population of agents, of 2,000 agents. This will not move, it's arbitrary, but it's just okay. That we calibrate. We take the age distribution on empirical data for 2020 from the United Nations. And now for each of our agents in the artificial population, we are going to assign them a number of contacts, and the age of each of these contacts. So for this, what we do is we go in the survey, in these data, we create, so let's say we have an agent in the artificial population of age 20, okay? And we go in the survey, we take all participants of age 20 in Italy, let's say we are interested in Italy. We collect in a list the degree of each participant of age 20 in Italy. And in another list, we collect the ages of all the contacts of participants of age 20. And now our artificial agent is going to pick, to draw from the distribution of number of contacts, empirical distribution of number of contacts, a number of contacts, And let's say it's 5, and then for these 5 contacts is going to draw an age in the empirical distribution of contacts of people of age 20 in the survey. So at this stage, we are like, we have 2,000 nodes. They all have a degree, that a number of links they want to create. And for each of these links, they want to create an age. And now we need to relate these links to each other. So the first thing we do is we follow a paper, a very recent paper by Gianluca Manzo and Arnoud van der Heij, where nodes sequentially create the number of links they desire with other available nodes, starting from the node with the highest desired degree and continuing in descending order. And every time a node has completed its, has created the number of links it is supposed to do, it's out of the pool of potential nodes to create links with. Okay, so, and at this stage we have a network that respects the empirical degree distribution, but not the age mix, right? And so for this, that's the last step of our algorithm. We are going to minimize, so progressively delete links and replace them to minimize a statistic that we compute, that is we call what we call the distance. It's not network distance, it's just follow this example. So here we have node I that is age 40, and he wants to create a link with someone who's age 17. And here we have node J that is age 20 and wants to create a link with someone who's age 34. And so this is the realized link, and we can compute the distance by taking the difference between the desired age and the realized age, the actual age of the contact. And our algorithm is going to, so here it's, in this example, we have distance for link ij equal to 9. And our algorithm is going to minimize progressively. It takes a while, but and to get a network that is actually close to the ideal network. Okay, and so over this network, we are going to simulate the spread of the disease. But just notice one thing is that actually we can, and that's what we are going to do, separate the different steps of our algorithm, and we can generate a network with the population age structure of the country, put the age mix, the inter-age contacts of another country, and put the degree distribution of a third country. So we can create counterfactuals network, and that's what we are going to do to isolate the specific aspects that we care about. So our model is very simple. The important thing is that it stays the same across different scenarios, across different networks. So we use a SEIR model. And the only thing is, because we saw that Germans have on average longer contacts, remember here, they have a longer contact than the other countries, the probability of transmission, the dyadic probability of transmission is calibrated on this average duration. That's it. So just to convince you that our algorithm performs well, this is the average and the median distance. So this statistic that I told. So for all the links in the network, this is what we get. So well, we can discuss, but I think it's reflecting, it's quite close. Notice that there is no reason to believe that it should be 0. Huh? It's not clear that the things should match perfectly. So the ideal network is not equal to, these statistics shouldn't be equal to 0. They have a minimum, but we cannot know it like this. Okay, so some results rapidly. So just to show you that the model is not completely unrealistic, this is how it looks like. So remember, it's a population of 2,000 nodes. This is the number of the average over all the simulations that we run for the Italian case, Great Britain, and Germany. These are the R0 in the middle of the peak. And just to show you, because we respected the degree distribution that is quite asymmetric, we have this phenomenon of individual variation in infectiousness. So many infectious individuals contaminate 0 others, 1, 2, and a few of them contaminate a lot. And actually there is empirical literature saying that it corresponds to the real situation. Okay, so now results. I will as I said, I can neutralize any aspect of of our 3 things: population, age structure, age mix, and degree distribution. And so yeah, that's what we do. We neutralize only we take always the same population age structure. So arbitrarily, we take the Italian one. And these are the cross-country differences just due to differences in network aspects. And you see that there are quite a bit of differences. Italy is clearly the most hardly hit country. In the absence of any form of lockdown or anything, it's purely theoretical. Now what happens if we also hold the degree distribution constant, but we change the inter-age mix. So this idea that intergenerational contacts matter. And actually, if we just take the differences in the number of people infected, we compare, so we have 3 comparisons possible. So this is England, it's not UK, sorry, it's Great Britain versus Italy, Germany versus Italy, and Great Britain versus Germany. We see that, I mean, maximum differences we get are like 4 or 5 individuals out of 2,000 persons. Instead, what happens if we hold the age mix constant, but we change the degree distribution only? And here we see that there are very, very large differences in the number of contaminated individuals. In particular, of course, when you compare Italy to Germany. Okay, and that's basically our conclusion. So I think in silico, we showed that everything else being constant, there are cross-country differences due to networks. But when we disentangle between the 2 aspects, so the density or the sociability of individuals and the age mixing patterns, it seems that it's much more the density, the sociability of individuals that matters than the age mixing patterns. That's it for me. Thank you.
Thank you very much, Luca. So until the questions are coming in, just don't be shy and raise your questions in the chat, and also you can raise your questions. You can raise your hand, and then we will see that if there is already a question. So Rafael.
Hi, Lucas. Thank you for this very interesting presentation. I just have a very quick question about your goals when reproducing the network. If I understand correctly, you're trying to reproduce essentially the degree distribution and the level of inner age contact in the network. I'm wondering if there may be other network characteristics like the level of clustering that may be relevant to your outcome, and if you're thinking of ways to reproduce those as well.
Well, thank you for this question. Am I thinking about this? Yes, I'm thinking about a way to implement this. It's quite complex because, I mean, I think if we would generate higher levels of clustering, we would get further away from the ideal network. And the second thing is we don't have data about the actual level of clustering in this. The only thing we had is like questions like, was it the first time you met this person? My answer would be this actually, is like, it matters mainly if there are reasons to believe that the level of clustering differs between countries. And I mean, if you can provide me evidence that there is, then yeah, it is a major thing we have to improve. Otherwise, I think it shouldn't matter so much. It would just slower the spread of the disease, but not generate cross-country differences.
Federico, you want to ask something?
Thank you, Károly. Well, thank you, Luca, for your very interesting presentation. Actually, I would like to follow up on Rafael's suggestion. I mean, you're right. Clustering might not be important if you are comparing and you assume that it doesn't vary, but doesn't it vary? I mean, if we're thinking intergenerational contact, can we not think of intergenerational ties also? I mean, sorry, if the level of intergenerational contact is not dramatically different from one country to another, then we can think that within generation contact might be the one who could be modeled as long-range ties. And those long-range ties, also relating to what Pierre has shown us before, is exactly what, you know, dramatically increases the rapidity of diffusion. So it might be the case that within generation contact, exactly those elderly people who spend the whole day at the bar playing cards and, you know, these are exactly the one, maybe more than intergenerational contact, that lets the virus spread from one family to another, which in from a structural point of view means from one cluster to another. So then, if this is correct, then cluster does matter.
Yeah, I see your point. Yeah, I think you're right. Well, I'm thinking about these things, obviously, but yeah, the cost of implementing this is just getting networks that would be further away from the ideal network in terms of age mix. But yeah, I'm going to do something in this direction. Although I think the differences are so massive in what we saw that I'm not sure even a super high level of clustering in Italy would change the main message, that is the density that matters much more than the age mix.
Okay, thank you. Christopher, maybe you can have still a short question.
Okay, yeah, a question about what you were doing with the polymod data. Was that giving you the number of neighbors each person should have with people in a particular age group, so the degree, or was it giving you the number of contacts with people in that age group? Now, if it's saying I've got 5 contacts with people in this age group, could be 1 contact with 5 different people, or it could be 5 contacts per day with the same person each time.
Yes, no.
And of course, make a big difference when you come to disease transmission.
No, you have identifiers for the contacts, and we take those that are not the same. So it's really the number of different people they met.
Okay, thank you very much. I think there is still a place in the chat to continue the discussion. So I saw that Filip also had a question or comment. So I'm sorry about not giving the word, but we have to move on. And then our next speaker is Blanca González from Stockholm University. And this is going to be something completely different.
Yes. Exactly. We completely changed the topic from COVID to fish. Let's see if I can share a screen. Yeah. Do you see and hear me well? Yes. So yeah, so thanks so much for inviting me here. I'm Blanca González. I'm a PhD student at the Stockholm Resilience Center in Stockholm University. And I'm going to present here this work that is well, still a work in progress, that I have been working with my supervisors that you see there, and you might recognize some of their names that have been in this social simulation week or presented in this week. And the work I'm going to present is well, about combining and how we combined network analysis and agent-based modeling to better understand the influence of small-scale fisheries trade networks. Yeah. So the aim of our study is to understand the role of trade networks among different types of traders and their interaction with ecosystems for the resilience of fish provision. So what we are interested here is in understanding these trade networks as social networks, but also recognizing that they interact with different fish populations. And the dynamics of the fish populations will also affect what occurs in the network. And we define the resilience of fish provision as the capacity to provide, or the capacity of this system to provide sufficient food while dealing with variability and uncertainty, in this case, dealing with environmental fluctuations. And we operationalize this resilience in 3 different outcomes. That is what we are measuring in our agent-based model. So this resilience on the one hand would be for individual traders, which in this case, it means the amount of fish supply and the variability of fish supply that these traders have. We will also measure resilience at the market level, thinking about the capacity of this market or the availability of fish in this market, in the markets. This would be, for example, looking on fish scarcity or fish waste, where the availability of fish is obviously defined in relation to the supply and the demand for the different fish markets. And the other outcome we will be looking at is on the exploitation level of fish stocks, which affect the long-term resilience, because if you have some overexploitation of fish stocks, obviously that would make it more difficult to provide sufficient food later on. So this is a bit what I mean to provide some context with the resilience of fish provision that we are interested in this model. And well, just to provide some context, this model is based on a study case which is the peninsula or the state of Baja California Sur in Mexico. And here, small-scale fishing occurs in many communities along the peninsula, and the fish that is fished in this diverse location is traded and finally sold to different types of markets. So the fish satisfies local demands, national demands, or even it can be exported internationally. And we are especially interested in these networks of how the fish is reaching from the different communities to the different types of markets. In order to do that, we use this mixed methods approach, which, as I was saying, in addition to agent-based modeling, we use network analysis, but also qualitative data based on interviews conducted in this region to try to understand the trading activities. And the specific way in which we use network analysis that I'm going to explain later on is by using exponential random graph modeling in a static way, which is a bit different of other talks, I think, of this conference, because in this case, we are based our study on an empirical trade network in this study case that is, and we only have data of 1 year. So that network data was collected in 2016, and that's the only data we have. Yeah. So this is the model structure, or the structure of our agent-based model, where we have first 2 regions, 2 fishing regions that you can see here. And in each of these regions, we have 2 fish populations. These fish populations can be 2 types of species A and species B, where the main difference of these species is that each of them will go to a different market. So we have species A going to market A, species B going to market B, and they cannot be substituted. And then we have what is the focus of this study, which would be the trade network, where we have different types of traders that we name sellers and dealers. And these different type of traders are based on a study, on the previous study that I mentioned, that actually empirically identified that some of these trading actors can both buy and sell fish, whereas other actors can only sell. So then we call sellers to those that can only sell and dealers to the ones that can buy and sell. And they interact in a trade network, which would be represented by these red arrows that we see here. Then every seller and every dealer can decide how much effort to allocate and how much to fish each of these two species to then sell to the different types of markets. And this network we have also observed that is more than just buying and selling a relationship, but these relationships are also what we could say committed or socially embedded. So that finding from the qualitative study is also what somehow supports the analysis of a stable network and on our aim, which is to look at the dynamics within those networks more than how links are created or deleted for this specific study. Then we also have different external dynamics that will affect how much fish they can catch, which would be different model scenarios, because at the end we are interested in knowing how the actors in this network deal with different fluctuations. So we bring externally different environmental fluctuations into the system. And now to briefly mention what are the activities that occur in the model and that occur within these trade networks. We have the model process here, where we can see two main types of activities. One here in orange, yellow, that would represent the trade process, and in blue it would be more of these interactions between the traders and the fish species. So starting from here, we would have a given market demand, and then the dealers in this network, this type of traders that I mentioned, are able to ask fish to their peers in their network depending on how much they need, and also taking into account that they know how much fish they got in the last time step. So based on that, they will ask fish to each other, and then we assume that traders in the network will take into account that information in order to take the decision of how much fish of one species to fish versus the other species, because they have a limited effort that they need to decide every time step how to allocate between the two species. So after they have taken that decision, they would go fishing, which will affect the fish stock, like the population level, and will give some catch to the traders. After the traders have the catch, they will then trade with each other within this horizontal network in order to satisfy each other's demands. And finally, they will sell horizontally to the final markets. So these are the activities that are happening. And I want to also briefly mention that these specific activities are, the way we specify these activities are based on this qualitative data that I was mentioning before. So it's informed by the analysis of qualitative data in the best possible way, which also relates to I think a session that happened on Tuesday morning in this conference, and help us a bit inform the dynamics that occur within the trade networks. Yeah. So then in order to analyze the model and answer our research question, which was mainly about how these networks can provide food while dealing with different environmental fluctuations, we set up different scenarios. We have scenarios varying different environmental changes, but for this presentation, I'm going to illustrate one of these scenarios, which would be seasonality. And as you see here, seasonality means that basically one of the species in one region will be removed somehow, or actors won't be able to catch that species for 6 months of the year, for every year. So this is like one example of an environmental change that we include in the model. And then what I mainly wanted to discuss here is how we build or bring different experiments, different network experiments in the model to try to understand the effect of different network structures. So in order to do that, we we use 3 theoretical network structures, which are mainly used to understand the model, but also for comparison, and 3 empirically informed structures. The theoretical structures are obviously, well, actually a no network, so a system where traders don't trade with each other. The complete opposite scenario, where every trader can buy and sell from each other. And of course, we also have a sensitivity analysis with a bit of a less extreme case, varying the number of links and so on. And then we have also quite an interesting network where we just have pairwise relationships between the traders in both regions, as you can see illustrated here. But what we think is really interesting is to try to think about empirically informed structures and what are the different outcomes generated by those. So in order to do that, we build different empirically informed network experiments, what we call them. And we do that based using exponential random graph modeling. So in this case, most of you might be familiar with exponential random graph modeling, as I have seen in other presentations. So basically, I'm not going to go in detail about this method, but we are basically trying to understand and explain an empirical network that I said collected in a previous study. And in our case, we think that the trade network will be influenced by different network formation mechanisms, we can think, or micro-level configurations, which would be the density of the network, the reciprocity, which is the tendency of the dealers, for example, to buy and sell from each other reciprocally, some centralization measures on how some actors might have a certain tendency to accumulate buying relationships or selling relationships, or many selling relationships to others. And we also think, and this is quite an interesting component, we think that an attribute of the trader can be particularly interesting to explain this network structure. And this attribute is owning a warehouse and having market access, thinking that traders that have those assets, let's say, they will have more tendency to buy relationships from others. So based on this, then we have the empirical structure, and based on the empirical structure, we create, also using the exponential random graph model, we estimate this network and get several networks, simulated networks that resemble somehow the empirical network. And here I'm just showing one representative of this set of networks. So we use that to build one of the network experiments, which would be similar to the empirical network. But we go a bit farther, and we also try to change actually one of the parameters of our exponential random graph model. And in this case, the centralization scenario, the centralization mechanism, to try to think on a hypothetical scenario, which would be like, well, what if traders would have less tendency to accumulate these relationships in a way? So there wouldn't be so much of these, let's say, very powerful traders that tend to accumulate a lot of relationships. And then we get a network in general, or a set of networks with lower centralization and also different characteristics. And this has been a bit exploratory, so I'll be happy to discuss about this more. I think it has some relationships with some of the talks that Christian was talking on Tuesday, I think. There's definitely ways to do this a bit more systematic, but here is just one example on how we just change one parameter that would generate the network to create a different set of networks that are then used as input for our agent-based model. And then we also create another network where more radically we just think, okay, what if this attribute of the traders was not important at all for explaining the network that we have? And we actually see that when we remove that mechanism, we get some networks that are quite different, and they don't really manage to capture the role of the different traders that we see empirically. So here is a network with much more dealers than what the empirical network would have. And we also use that in our ABM. So basically, through the agent-based modeling of these networks, we see that there are some differences in the capacity of traders in these networks to provide, well, for the resilience of this fish provisioning, right? So there is a difference in how, for example, they manage to reduce the fish scarcity in the markets facing environmental fluctuations. But I'm not going to go in detail for the results here so that we have some time to discuss, and just end up with a conclusion on how basically the use of network analysis and exponential random graph modeling help us understand a bit more these empirical trade networks. And it gets a bit to try to link these network formation mechanisms to different network structures, but then the agent-based modeling is especially useful to model the activities that occur in these networks and link them to system level or macro level outcomes, which in this case we mean by outcomes related to the resilience of fish provisioning, and also thinking on how those outcomes might affect the activities that occur in the network. Yeah, so thanks so much for listening, and yeah, I'm looking forward to questions, and also if you are interested, here is my email to further discuss this approach. Yeah.
Thank you very much. It was an excellent presentation. Filip has a question.
Yes.
Hi. I was just wondering if when you talk about changing a parameter like centralization, I forgot whether it's in degree or out degree centralization, whether you're changing it for the sellers, the dealers, or both?
For both.
Okay, because
yeah.
The question is, what do you want to do when you're saying these things? I think it's a different thing when it's the sellers that actually change their centralization, or it's the dealers that change their centralization.
Yeah, well, actually, in theory, it could be changed for both, but what I'm specifically interested in changing is the centralization of buying relationships. And actually, in fact, the dealers are the only ones that can buy fish.
Okay.
So in that case, actually, what we will be looking at is mainly the dealers' centralization. So, and I think that makes sense also. And you're completely right, that is different. And for the dealers, it makes sense because you would think, what if there is kind of less powerful actors buying from others? Mm-hmm. Which is what I wanted to look at in that case.
Okay.
Yeah. Thanks for the question.
More questions coming in? Anyone? So I have a question about because you have had this cycle that the whole actually the fishing and also the market demand is updated as a reinforced by each other actually. And do you consider the time that it takes, because it might be very different, and there, of course, different circumstances might impact how much does it take to that this cycle is actually completed?
Yeah. So in the model we have it as a weekly timescale basically, but this is a bit empirically informed by just thinking on this study case and what fishing and trading implies. So basically that fishers go fishing and then they have to trade, and then this is transported to the city and bought and sold. So that is a bit what we have thought about the timing, and there could be a bit of a delay between the fishing and the trading there. So that's why it's like weekly timescale. I don't know if that was the question. Yeah.
More questions?
It was clear.
Well, mine is more a comment than a question, and probably quite similar to the one that Filip told you before, but also having in mind Christian Steglich's presentation on day one of this workshop. I was wondering, when you manipulate the one parameter in the ergon model, how does this, I mean, how legit is to do this without having some at least theoretical idea of how the other parameters vary at the same time.
Yeah.
Which is an open question, actually. I mean, from a strictly statistical point of view, it's probably that. I mean, you shouldn't do it because we know that those parameters are correlated with each other. But I don't know. It might still be legitimate because you have some theoretical idea in mind that you're not really interested in estimating the variation precisely, but still just look at qualitative differences. I'm thinking out loud.
Yeah, and I think that is a very valid point. I mean, I have been thinking that with myself a lot, like how to deal with the fact that when you change one thing, you change many. So at the end, it is very difficult to know if we see different outcomes in the ABM, it is because we changed that centralization or because by changing centralization, also density decreases. So for example, so I get that point. And I think it would require probably a more robust sensitivity analysis of changing, like as Christian was showing a bit, changing how, try to understand exactly what is changing in the network and trying different networks where we make sure that maybe only one thing changes, but that's really hard. So yeah, a bit more, being more thorough in that process is probably needed. But I think it also depends on what, as you say, what are you using it for, and what are you, how do you interpret your results? So yeah, thanks for the comment.
No, you will actually, if I may elaborate on it. I'm going to go a bit provoking, but why not just going with an agent-based model and you know, and starting from theoretical assumptions, maybe empirically informed by the networks you observe, but not really, you know, one-to-one calibrated on the ergom estimates. I'm a big fan of the interaction between ergom and ABM. But I don't know, maybe sometimes agent-based modeling in itself can do a lot alone.
Yeah, I agree. No, and thanks so much for your point. I mean, I think we have been thinking quite much about that, and definitely, I think, for example, this approach doesn't, for me, it doesn't make much sense if you don't have together a sensitivity analysis using maybe more, let's say, archetypical structures to really try to understand one by one what's going on. So we also have like this an Erdős-Renyi kind of random network where we just change the density or change only the proportion of trader types. Like, I think definitely there is a lot of things we can learn without this link to the ERM and the empirical network, which is a bit complicating things a bit too much. But on the other hand, it does allow us to maybe create scenarios that have a little bit more connection with empirics, because we know that empirical networks are not random networks, and they are not the small world networks, and so on. So this helps us somehow to bring in a bit more of empirical realism in a way. And then the ERM, I think, really allow us to know, okay, what exactly is changing from one network to another. Not only by doing the ERM, but also by simulating and looking at all of the network characteristics and kind of comparing the motifs of the different networks and so on. So yes, it's a good question. It's an interesting thing to reflect on and to think about.
Okay, thank you very much. I think it was an excellent answer. At least I like the answer. And also I like the presentation, and thanks very much for the questions. We have to move on as there is actually a slight typo in the program, but as yesterday and also the day before yesterday, the next presentation is supposed to start at 3:45, as we have to finish by 4 p.m. sharp. As there is a plenary afterwards, after the session. So I would like to introduce you the next speaker, Simone Gabriellini from University of Trento.
Let me unmute. Okay, let me share my screen. Okay. Okay, perfect. So I'm going to talk about this project, network effects on tax compliance. So this is a project that we started, Famino, myself, and a couple of economists from the University of Brescia a couple of years ago. And the idea was to try to understand how we could use an agent-based model to understand, to explore how social networks can affect the decision of the agents on tax compliance, basically on the decision to declare all your income or just part of your income. Now, of course, this is a problem for which there are very few empirical data. So I'm not going to show you an empirically calibrated model, but just very, very briefly, let me say, of course, tax evasion is a problem because it brings less revenues for every government, and less revenues means less quality and difficult for public and social services to be sustained. And of course, this ignites a vicious circle where those that report their income regularly and those under the poverty line who depend more on these services are the more affected by this problem. And this brings also long-term implications like less investment, which contributes to perpetuate the social and economic inequality. And at the end, it erodes the credibility of public institutions and weakens the moral foundation of society. Now, 2011, just a quick heads up on the numbers. We're talking about just in the US, 2011, the underreporting was estimated in about $500 billion US. Tax evasion in Europe is about 20% of the GPD. And also we have like 270 billion in unpaid taxes in Italy alone. So of course, every government tries to increase the efficiency and the efficacy of the audit process by collecting more detailed information on taxpayers from different sources, mainly nowadays digital, and also using creative nudges, experiments to trigger moral instincts and social motivation in taxpayers. However, there's still the need for explaining the economic and social determinants of tax compliance and evasion better. So the key is to increase these, to help policies to be more, control policies to be more effective. But there are, you know, on this topic, different streams of research in economics, in sociology, in psychology that have developed relatively isolated from each other. So without an effective integration that would be required to understand this complex problem. Now, what is the puzzle here? The puzzle is that basically all the models that deal with tax evasion look at tax evasion as a decision made by rational individuals that respond to benefits and costs under given constraints. And the very interesting thing in this situation is that predictive results, they tend to overestimate the actual level of tax evasion. And this is also, I mean, this point is also worsened by the fact that actually there is a relatively high level of compliance, at least from what we observe empirically in different countries, compared to the typical level of institutional enforcement. And of course, the level of institutional enforcement is like is directly tied not to the willing to control people, but to the finance that you have at your disposition to pay for the process of doing the due diligence on tax declaration. So this is a very interesting point. So the idea here would be that the agents are boundary rational. They follow heuristics-based satisfying criteria rather than optimization. And they would adapt and learn both from the experience and their own experience and from observing others through like trust networks. Taxpayers are also heterogeneous in their strategic decision, in their social context, and which means the exposure of others to others' behavior, and they can influence each other. There is a stream, a very recent stream of literature with on tax evasion that uses agent-based modeling, I mean, the main idea in this situation, these agent-based models almost all have like taxpayers, agents that have different strategies or are embedded in specific social networks. And there are basically two lines of dealing with how tax compliance or evasion is done. There is a deterrent model which is focused on enforcement. Taxpayers are seen as profit seeker, and the idea is to explore what is the optimal level of enforcement. So like audit probability, tax percentages to improve tax compliance. And then there's another stream that is called the accommodative model, according to which taxpayers are seen as susceptible to moral motivation. Okay, so this is called like these models are called are focused on tax morale, where taxpayers are they want to abide social norms. So let me just say a couple of things very brief on this. I mean, I'm not going to review all this literature because it's way out of the scope of this thing, but just so you understand, the point of tax morale is basically emerged from this question: why different countries that has different that has the same level of institutional enforcement experience different tax compliance rates. So maybe tax morale, not simply enforcement, play a role in the decision to comply. And this evidence of this was found in a variety of different national social surveys. On the other hand, we have a lot of literature that deal with enforcement. So trying to understand what is the optimal level of audit probabilities and tax rates in order to get the best to optimize compliance. Now, in all of these models, there is almost always agents that belong to different strategies. They do not evolve their own adaptive strategy, but they are just assigned when they are born to different. They can be like honest, imitative freeriders, where honest are people that just maximize their utility by complying to social norms. The imitative, they're just happy to do what others do. And then you have freeriders that just try to, maximize their own utility by paying as little in taxes as possible. So this is this stream of research slowly added networks to the mix and started to examine how different social networks could be able to broke different level of tax compliance. Now, let me in this last 10 minutes say something about what we wanted to do. We wanted to use a more robust tax evasion model. So we wanted to borrow something from the field of tax evasion in economics and bring that machinery into an agent-based model that uses networks in order to see to have a more grounded and robust model, not a naive approach to building agents in this kind of concept, for this kind of problem. And we, of course, we collocate our model in the enforcement literature. But we also want to have this kind of rigor when it comes to how agents decide to the optimal consumption or the optimal rate, the optimal compliance that they want, according to what they produce. We also want we don't want agents that belong by definition to specific classes, so they are all alike. And then they, of course, are embedded in networks, so they will have different kind of experiences according to who they are connected with. But they are not by design honest or imitative or whatever. We relax, of course, the assumption of full rationality, and we don't have I mean, our agents are not super heterogeneous, but they experience different level of risk propensity, and they experience, of course, different social realities, let's say, so according to how many people they are connected with. And also and this allowed us to consider, I mean, heterogeneous agent behavior and social network structure components in understanding the dynamic of tax evasion in this aggregate population over time. So we basically, for each agent, deciding how much to evade is a decision that is subject to uncertainty, to a specific level of risk propensity, and also it's subjectively influenced by previous experience. So what is their own previous experience and what they can learn from, see from others, from their neighbors. So we have basically agents that are this model belongs to those called like constant relative risk aversion family, in the sense that the relative risk aversion of the agents is independent of their wealth and capital. But let's go down to see how the model works, because there's very, very little time. We have a population of end taxpayers. They have an initial capital. They have a productivity level, which is the same for everybody for the results that I'm going to show. They have this risk adverse value, and they will at each time step calculate a lambda, which is a subjective probability estimated using network effect. And then there's, of course, each of them will have a number of people they are connected with, and they will have also memory, so the ability to remember the past. Okay, so the agent can remember what happened this year and know what happened this year for the neighbors, and then go back in time up to 5 years and 10 years. So we in a way, we emphasize the role of social limitation in this way, just looking at other neighbors. But on the other hand, the model also assumes that taxpayers build their own weighted audit probability, like in there's a stream of literature in the enrichment, in the enforcement stream, where agents look at their personal history and that of the neighbors at the same time. This is one thing that we also do, is that we check we run the same simulation in two different network contexts. One is the random networks, and one is the small one networks. And of course, random networks and small one networks have little to do with the real networks that we experience. But these two models are a good baseline for the complete randomness, and the other one is the best approximation we have to something that has like short path and high clustering. So basically, we test also, or we do this kind of test constraining on a specific number of degree of connections, but with the difference that in the random and smaller topologies, these kind of connections or wires in a different way, and we will see that this implies that random smaller networks are more suited to enhance whatever is going on in networks. So they have like an eco effect on what is the predominant thing. So like compliance and not compliance. Let me go down to the results in this 3-minute slide. Just a brief thing about the scheduling. So every agent start with a capital. Okay, so sum of money that we give to the agent. Then he produces a gross income from the capital due to a productivity level. Then he decides how much to evade. Then he declares the visible income and pay taxes on that. Then he gets audited. I mean, there's a probability that will pick a certain percentage of the population. And if the agent gets audited, well, if he evaded, he pay a fine proportional to the evasion. And also he remembers it. And if he didn't evade, then all is fine, and he also remembers it. Then at this point, the agent decides how much to consume. And at the end of the day, the agents just say, okay, how much capital do I have left after all these things? And then we go to the next year. And we do this for 40 years. Actually, the simulation lasts for 70 ticks, where every tick is a year. For the first 30 ticks, we just throw them away, just to go away from initial condition, whatever it is that can perturb the model without any reason, because there's no empirical calibration here. Okay, so we try to forget about that. Let me just say what happens here, how we decide about tax evasion. So the fear of evading is proportional to the presence in the neighborhood of people that have evaded and got caught. So if you see people that did evade and got caught, you get scared of that because you don't want to go in the same direction. And of course, the same is also true. There is an appeal for tax evasion that is proportional to the presence in my neighborhood of people that have evaded and didn't get caught. So lucky evaders, basically. But we are waiting, actually, we are still studying this thing, but we are weighting these two probability in a different way, because we want our agents to be more scared of bad example than pleased by positive example. So let me show you something that we have seen from the model so far. One of the things that is in the literature is that more enforcement leads to less evasion. Okay, so this is it looks like in our simulation, more enforcement actually brings compliance down. Okay, so especially when audits, which is the size of this point here, are more frequent. So more enforcement actually brings compliance down. So it looks like our agents where they receive a lot of control, they tend to compliance less. Instead, what is interesting, increasing the audit probability of or lowering taxes, but lower tax evasion. Okay, so this is an example of on a 5,000 nodes, small word network with a neighborhood size of 8. So every agent has 8 possible neighbors. And we have no evidence that lowering tax will increase compliance. But on the contrary, the model shows that if you lower taxes, you increase evasion and decrease compliance. Instead, what about high compliance with low enforcement? So agent compliance, we have an audit probability of 1% here. Agent compliance this is interesting because this is the only thing that we have that can be like not calibrated empirically or validated empirically, but we have a lot of surveys that says that the compliance, empirical compliance is something between 60 and 8%. With an audit probability of 1%, and we sort of produce results that are in that kind of space. So, which means nothing actually, but we are happy that we are somewhat in the right area. Okay, and then think time is over right now, but just wanted to tell you that as the neighborhood size increase, also compliance increase. So, and these might be a consequence of being this is irrespectively of network topologies, but as the neighborhood size increase, all agents are more willing to declare taxes, which is, it's also, I mean, it happens in both topologies. It happens more in the small world topology. But one interesting thing is that, of course, the size of the network is negligible. Okay, so it doesn't really change that much, but the size of the neighborhood has an impact. So at this point, well, memory, of course, is another thing that we looked at, and it looks like more memory of the past as an effort of pushing compliance out. Okay, so because you're able to remember more of the bad things that happen around you, so you are still more aware of what happened. So conclusion, we're still in progress with this thing, but we think that our model like sort of unifies some results that we have found in the literature on IBM and tax evasion, and we have pairs with a rigorous economics model of consumption and compliance that there's in economics literature. We add memory to this equation here, and we also have a very rigorous assessment of how network topologies impact on tax compliance. And this is all I have, all we have for up to this moment. The research is still in progress, but until that, I mean, thank you very much for your attention.
Thank you very much, Simone. There are already questions from the audience. So maybe, if you don't mind, Andreas, I give the floor first to Luca.
Yes, thank you. Thank you for the presentation. It was very interesting. It's a very simple question. Was saying, is it realistic to assume that someone who evades will also communicate it to its contacts, its professional contacts?
Yeah, good question. There's actually literature on that, like a couple of papers that investigate how this kind of evading schemes are shared on trust networks between people that are actually evading.
Okay, thanks.
Okay, now Andreas.
Hi, Simone.
Hi.
Very interesting. I just didn't get how the model generates this result that enforcement reduces compliance. Or did I misunderstand this? Maybe you can explain.
Okay, more enforcement brings compliance down. I think that this is the most counterintuitive result that we have, and I don't actually have a good explanation for you because we are still trying to understand how this result is generated by the model. My guess at this point is that and this actually, I mean, it's not it's very difficult. It's very difficult. I mean, I've tried many times to find a good explanation for this. The only thing that I can think about is that when you increase enforcement, you actually increase the fine that you're paying. Okay, in this case, and the fine and the taxes that you pay. So it might be that actually that this somewhat brings the agent to weight less the fear of being caught. This is my understanding of that. But actually, I let's say reserve the right to give you this answer again, because I'm still puzzled myself with this.
Okay, thank you.
So, yeah. I mean, Flamino is saying this thing that in the chat, that because when they actually do something, when they actually decide how to evade and how to consume, and they are actually, and this is something that Flamino and I are trying to, push inside the model. They are actually looking at a time horizon that is larger than, I mean, it's difficult to disentangle this economic view where you have these agents that knows everything and has the whole horizon of in front of himself, just to an agent that is in a bounded rational situation. So that might be one of the reasons that we see these counterintuitive results.
Thank you very much, Simone, and thanks, Andreas, for the question. And also, I would like to thank everyone for the participation and for all the presenters. It was a very, very interesting and very good session, and it was a very nice free days actually that we spent together and on this topic. I think it was very productive, and also we learned a lot from this. So. I hope you are going to enjoy the rest of the conference. We are just a couple of minutes, couple of seconds late, but it's still a good time to catch up Petra's keynote speech. So thanks for all of you, and see you later.